Hello, I am the moronic Mr. Daycock, and today I am going to be teaching you how to prove that closed forms satisfy a recurrence relation by induction. Now, recurrence relations lend themselves to induction very, very nicely. And the reason that they lend themselves to induction very, very nicely is because they are basically already using the concept of induction to create them. We're taking one thing and taking the step to the next thing. So it works really, really well. So first of all, we need to deal with the base case. Now the base case for the recurrence relation is just what you're given. This is the recurrence relation, and our base case for the recurrence relation is that we have, that says U0, it should say A0. We have that A0 is equal to 7. Now for the closed form, which is what we need to prove, the closed form here, we have that A0 is equal to, let's make it clearly look like a 7, 1/9 of 71 times by 4 to the power of n, but of course our n is 0, 4 to the power of 0, minus 6 times by 0 minus 8. And then simplifying this, we get A0 is equal to 1/9 of 71 times 1, because 4 to the 0 is 1, minus 0 minus 8, which gives us A0 is equal to 1/9 of 63, which is equal to 7. And so we have the recurrence relation is equal to the closed form for n equals 0. Great, so we have that initial base case. Now we need our assumption. Our assumption is going to be assume closed form satisfies recurrence relation for some n equal to k. Except if we go up here, we notice that this is n minus 1 and we want it to go to n. And so it's going to be a little bit nicer for the form that we have to write this as n equals to k minus 1. So what we have that a k minus 1 is going to be equal to 1/9 of 71 times by 4 to the k minus 1, because we're using k minus 1 here, minus 6 lots of k minus 1 minus 8. And then we want to simplify it just to make it a little bit nicer. A k minus 1 is going to be equal to 1/9 of, that negative 1 is going to come out as a divide by 4, 4 to the k, minus 6k, and then subtract 6 multiplied by negative 1 is going to be add 6, so we're going to altogether get negative 2 from that. And that is our simplified form that we get from our assumption. And then we want the inductive step. And what we want is that AK is equal to 1/9 of 71 multiplied by 4 to the k minus 6k minus 2. That's what we want. What we have is, of course, this. We have that. So we're going to use the recurrence relation because we also have the recurrence relation. The recurrence relation is the original thing that we were given, and we want to show that the closed form works for it. So we have the recurrence relation, and we want to plug our assumed closed form into it to get our AK. So our recurrence relation is AK is equal to 4 lots of AK minus 1 plus 2k, if I am not mistaken. Let's go back up to the top. Yes. So from this information, we're going to actually just plug in the thing that we have, which is our assumption. We can't plug in this yet because we don't know what that is. So we're going to substitute in our assumption And so we're going to get that AK is equal to 4 lots of 1/9 of, but let's make that a little bit simpler. 4 lots of 1/9 is 4/9. 4/9 of 71 over 4 times by 4 to the k minus 6k minus 2. And then on the end we have plus 2k. And then from there we're going to get that AK is going to be equal to, let's expand this out, 71 times by 4 over 9 times 4, lots of 4 to the k, minus 6 times by 4 over 9, k, minus 4 times 2 over 9, and plus 2k on the end. So that's just expanding out the brackets there. And from here, well, we can do some nice cancelling there. That cancels out nicely. We get AK is equal to 71 over 9 multiplied by 4 to the power of k minus 24 over 9k minus 8 over 9. And then we've still got the plus 2k on the end. Now what we're going to want to do is we actually have 2k terms here. So we want to combine those. 2k is equal to, let's get it common denominator, 18 over 9k. And so when we combine those two terms, we're going to get AK is equal to 71 over 9, lots of 4 to the k, minus negative 24 over 9 plus 18 over 9 is negative 6 over 9, k, minus 8 over 9. And now we want to factor out that ninth. It's a ninth in every term. We get AK is equal to 1/9 of 71 multiplied by 4 to the k minus 6k minus 8 as required. And then we just go to our conclusion. Closed form satisfies recurrence relation for n equals 0, and if satisfies for n equals k minus 1, then satisfies for n equals k. Hence, by induction, true for all n greater than or equal to 0. And it can be equal to 0 here because we started at n equals 0 rather than starting at n equals 1. Okay, so that's first order. Let's look at an example now of second order. Prove that by induction that un equal to 2 root 3 of sine pi over 3n satisfies the recurrence relation un plus 2 is equal to un plus 1 minus un with u0 equal to 0 and u1 equals to 3. Now, because this is a second order recurrence relation, we actually need to start with two base cases. And that's the base case u0 equal to 0 and u1 equal to 3. We need to check both of those are satisfied by the original thing. Because remember, a second order recurrence relation doesn't make any sense if you only have one of those. And so let's take our closed form. u0 for our closed form is going to be equal to 2 root 3 lots of sine of pi over 3 times 0, which is equal to 2 root 3 times by sine of 0, which equals 0. And let's try u1. I wrote 1 there, it needs to be 3. u1 is equal to 2 root 3 multiplied by sine of pi over 3 times 1, which is equal to 2 root 3 times by sine of pi over 3, which is equal to 2 root 3 multiplied by root 3 over 2, which is indeed equal to 3. And so we have that the recurrence relation is equal to the closed form for n equals 0 and n equals 1. And again, this here is a second order one, so our assumption step is going to be assume closed form satisfies recurrence relation for, let's go up here and check what we've got. Well, we've got un and un might plus 1 to get to u2 for n equal to k and n equal to k plus 1. Because it's second order, we need both parts. We need 2 steps. And so we have that uk is equal to 2 root 3 times by sine of pi over 3k, and that uk plus 1 is equal to 2 root 3 of sine of pi over 3 lots of k plus 1. And now we want to use the inductive step. And we can use the recurrence relation and assumptions and so we get that uk plus 2 is going to be equal to uk plus 1 minus uk, which gives us, that's equal to 2 root 3 lots of sine of pi over 3, need an extra bracket there, of k plus 1 minus 2 root 3 of sine pi over 3k. And hopefully we can see immediately that we can do some factorising. We get 2 root 3 lots of sine, and I'm going to expand the inside of this, root 3k plus pi over 3k plus pi over 3 minus sine of pi over 3k. And that's just factoring out these 2 bits out to here. Now, at this point, we need to use our angle addition formulas. Which is that we have sine of a plus b is going to be equal to sine of a cosine b plus sine b cosine a. But in this case, we have a equals pi over 3k and b equals pi over 3. And this will allow us to split it up into a form that's more manipulatable. And so that green part is going to become sine of pi over 3k cosine of pi over 3 plus sine of pi over 3 cosine of pi over 3k. Cosine of pi over 3 is a half. Sine of pi over 3 is root 3 over 2. And so this is going to become a half of sine pi over 3k plus root 3 over 2 cosine of pi over 3k. And now all we want to do is plug that, substitute that back into here, and so we're going to get 2 root 3 lots of 1/2 of sine of pi over 3k plus root 3 over 2 cosine of pi over 3k minus sine of pi over 3k. And here we actually have a like term. And so this simplifies to 2 root 3 lots of root 3 over 2 cosine of pi over 3k minus 1/2 of sine of pi over 3k. Now, if we think carefully, we want u of k plus 2, and we want that to be equal to 2 root 3 sine of pi over 3 times by k plus 2. So what we want, we already have this 2 root 3. So what we want is that this is equal to this. So we want sine of pi over 3 lots of k plus 2 to equal root 3 over 2 cosine of pi over 3k minus 1/2 of sine of pi over 3k. So in this case, we're just going to use our double angle formula again. Expand this inside, so we get sine of pi over 3k plus 2 pi over 3 is equal to all of this. And then expand, well, we want it to be equal to that, so we're going to put a question mark there. So let's actually use our double angle formula. We end up with sine of pi over 3k times by cosine of 2 pi over 3 plus sine of 2 pi over 3 multiplied by cosine of 2 pi over 3k. And as it turns out, cosine of 2 pi over 3, you can use your calculator for this, is absolutely negative 1/2, and sine of 2 pi over 3 is root 3 over 2. And so what we get here is this is indeed equal to root 3 over 2 cosine of pi over 3k minus 1/2 of sine of pi over 3k. And if it works one way, then it must work the other. So this can be substituted for what we want. And so going back to our original statement, we get uk plus 2 is equal to, substituting this in, 2 root 3 lots of sine of pi over 3k plus 2 pi over 3, which is equal to 2 root 3 lots of sine of pi over 3k plus 2, as required. And then we just conclude. And in this case, we do need to remember that we are dealing with both two starting points. So closed form satisfies a recurrence relation for n equals 0 and n equals 1, and if it satisfies for n equals k and n equals k plus 1, then satisfies for That doesn't look like an and, that looks like an and if satisfies for n equals k and n equals k plus 1, then satisfies for n equals k plus 2. Hence, by induction, our closed form satisfies recurrence relation for all n greater than or equal to 0. Thank you very much for watching. That is 2 examples of proving recurrence relations with induction, or proving the closed forms of recurrence relations with induction. The second one certainly got quite complicated there, but the inductive principles are still the same, and hopefully my change of colour made that a little bit understandable. Obviously, if you are still struggling, feel free to go back through the video or ask me questions in the comments. Thank you very much for watching, and I'll see you in the next video.